Good morning, everyone. Just give me a minute. Hopefully you can see my screen. We left off last time talking about electron configurations and abbreviations. So let's just to refresh, let's do another one of those. Clear this out. So I want you to do the electron configuration for Br, bromine. I want you to do the full and the abbreviated. Okay. And by abbreviated, I mean using the noble gas. So make sure you have a periodic chart. Let's do that. Okay, so for these, if I look on my periodic chart where bromine is at number 35. So the first one I want to do is the full electron configuration. So I start at the top of the periodic chart where hydrogen is, and I fill in the first shell. Now we're at the, we're in period 1 and we're in the S block. So I fill the 1s first. So 1s, and we fill it completely. Then we move to the next line where lithium is, and we're in the 2s block. And I have to fill that completely because we run completely through it. After the 2s, we go over to boron, and that's the 2p shell, and we fill that fully. Then we move to the 3s, and that is filled completely. And then we fill in the 3p, where aluminum is, all the way to argon. And then we fill the 4s completely. Now remember, we're going to do the next one we run into is 21 scandium. That's in the D block. D is always one less as far as its number is. So this is going to be the 3D. We fill that in completely. And we end up where zinc and gallium are. And so we're back up to the level 4P, and we fill in 1, 2, 3, 4, and 5. Okay. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. Sorry, that last 5 doesn't look very super scripty, but that's supposed to be the upper right-hand corner. Now, if we're going to do the abbreviated version, you abbreviate with the noble gas before, not after. So bromine is super close to krypton, I know, but we don't get to use krypton for the abbreviation. Instead, we have to use argon. And looking here, argon is this configuration here, from there all the way to there. So when abbreviating it, we can do argon in parentheses to represent this whole thing, but then we need to add the remaining stuff. 4s2, 3d10, 4p5. Any questions on that? No. Okay. Now I want you to do the electron configuration for, I want you to do the electron configuration for oxygen. The full electron configuration. So the electron configuration. And then I also want you to do the orbital diagram. The orbital diagram are those boxes, all right? So it's just taking the electron configuration and representing it with the boxes and the arrows. So I'll give you all 2 minutes to do that. And if you have any questions while you're working on it, just pop your mute off and let me know. Okay, so for oxygen, the electron configuration 1s2, 2s2, 2p, 1, 2, 3, 4, 2p4. Now, when we're doing the orbital diagram, that's where we do the boxes. So the S's is a set of 1 box, the P's are a set of 3 boxes, the D's are a set of 5 boxes. Boop, 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 boop. So this is the 1s. This is the 2s. And this is the 2p. When filling in the arrows, we're going to fill an up arrow and a down arrow. And fill an up arrow here and a down arrow here. And when we get to the P, remember that you've got to fill everything in singularly first, and then we double it up. So what I don't want you to do is up, down, and you leave this empty, because that's very, very lopsided in the structure of the atom. So instead, we're going to fill in an up there, we're going to fill in an up there, and an up there, and then we're going to go back and double up there. Any questions on this thing here? No, okay. So the orbital diagram is just kind of a pain in the butt to do of the regular electron configuration. The only additional step with orbital diagrams is making sure you're filling in singularly. So we'll head back to the slides over here. All right, so valence electrons are super important. A valence electron are the electrons that you find in the outermost principal shell. So you go and you look at your electron configuration and you find whatever shells have the largest number, those will be your valence electrons. Why are these important? Because valence electrons are the only electrons that are really going to be involved in chemical bonding. All the other electrons that are on the inner full onion layers, we would call core electrons. Core electrons are already in a satiated shell or a complete shell. Either they have 2 electrons or they have 8 electrons. So they're happy. So they don't need to do any bonding. Valence electrons, on the other hand, those ones in the outermost shell that aren't in a complete shell, are going to want to bond. And that's how we get compounds. So that's why, things like sodium and chlorine come together and carbon and oxygen come together. So let's look at the electron configuration for silicon. So silicon is 1s2, 2s2, 2p6, 3s2, 3p2. When calculating the core electrons from this thing here, what we see is that the lower numbers, so the 1 and the 2 here, are going to be core electrons. The 3 and the 3 are going to be valence electrons. So we add up the number of electrons that we have in our outermost shell. So in this case, I have 2 here and I have 2 here for a total of 4 valence electrons. So silicon has 4 valence electrons. Hey, look at your periodic chart. What column is silicon in as far as your main group elements? 1, 2, 3, and 4. It's in column 4, and it happens to have 4 valence electrons as well. Okay. So you could, if you want to, write these out to calculate valence electrons, or you can go with the much easier rule of thumb, which is column 1 has 1 valence electron. Column 2 has 2 valence electrons. This is different than charge. Okay, this is another piece of information you want to lay on top of charge. Column 3 has 3 valence electrons. Column 4, where carbon and silicon are, have 4 valence electrons. Nitrogen, phosphorus, they produce a -3 charge, but they have 5 valence electrons. Oxygen, 6 valence electrons. Fluorine column, 7 valence electrons. And then the noble gas column minus helium, those all have 8 valence electrons. And 8 valence electrons is known as an octet. It's very stable. It's a complete outer shell, so those things don't tend to chemically bond. So you're more than welcome to write the electron configuration every time you want to find valence electrons. Or you can just say, hey, how many valence electrons does sulfur have? Well, sulfur is in column 6, so we're going to go with 6 valence electrons. Let's look at Se. So selenium, which is 20, what do we have it is? I don't even know. Where are you, Se? 34, okay. So if we look at selenium, number 34, what column is that in? It's in the same column as oxygen and sulfur. So my guess is going to be that it has 6 valence electrons. Well, let's prove it by writing out the electron configuration. So there it is, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p4. Now, when you're looking at one of these electron configurations and we want to calculate valence electrons, we only look at the largest number. So there's 4 and there's 4. Remember what happens with D. D is 1 lower than its surrounding neighbors. So when we're doing Ds, we're actually filling core electrons. So it's sort of like we're filling the outer onion and then we start packing the inner onion and then we go back to the outer onion again. It is the way it is, just accept it, all right? So D is not included in valence electrons. So what do we have here? We've got 2 in the S and we've got 4 in the P, 6 electrons. What column is it in? 6 electrons for the valence. We're going to need to be using valence electrons a lot in the next chapter. So you want to be comfortable with calculating valence electrons by the column it's in. You're not going to want to write an electron configuration every single time. We good with valence electrons? If you're asking, well, how many valence electrons do the transition metals have? Well, like everything else, the transition metals vary, okay? So they can have a variety of situations. So I'm not going to stress you on that. So if we look here, here is the electron configuration of the outermost shell for each of these things. So here's the outermost shell has 1 in the 1s. Lithium, the outermost shell, it has 1 in the 2s. Sodium, the outermost shell, has 1 in the 3s. Obviously, there is more to the electron configuration than just the 3s1 here. It's got everything packed in before it. But what this shows you is that in column 1, there is 1 valence electron in the outermost shell. If we go into column 2, what we can see is there are 2 valence electrons in that outermost shell. That's why we get 1, 2. Let's go over to, let's skip a couple columns, 3, 4. Let's go to 5. Where nitrogen and phosphorus is, they all have this outer electron configuration that's very similar. The only difference is it's 1 number up. So there's 2 in the S and there's 3 in the P for a total of 5 valence electrons. Same thing here, 5 valence electrons, and it's in the 5th column. If we go down to noble gases, oh, look at that. Isn't that pretty? It's nice and complete. All filled in. The S's are filled in and the P's are filled in. Now, is there a P shell for the quantum number 1? No, there is no 1P. There's only a 1S. The P doesn't start until we get to the 2. So that's why helium can be stable with just 2 electrons. But all the rest of them have the 8, the 2 in the P and the 6, or I'm sorry, the 2 in the S and the 6 in the P. So yeah, I don't know why the slides are now starting to talk about the S, P, and D block, because that was so much more useful earlier on. So they're talking about, hey, here's the S block, here's the P block, here's the D block. Hopefully we're all good with that. There's the F block. So the number of main group valence, or the number of valence electrons in the main group, you can find from whatever the column number is. It gets a little different and a little sticky with transition metals. There are some exceptions, and we're just not going to go over that, okay? Just, you can leave transition metal stuff for electron configurations. You can leave the exceptions for now. All right. We've already gone over all this, SP, all that stuff. Great. So let's talk about the explanatory quality of the quantum mechanical model. So we said sodium likes to form an Na plus ion, right? Because it's in column 1, it likes to form an Na plus. Fluorine likes to form an F minus. Why is that the case? Well, I'm gonna go back over to our board here. Let's clear this out. Let's do the first one we'll do is Na plus. So hopefully by now you guys are starting to get comfortable with the idea that this is not the same thing as this, right? This is sodium with a +1 charge. Let's even just go over it. So sodium, as far as protons are concerned, if it's sodium, it will always have 11 protons. Protons, 11. How many electrons are in this situation where we have a ground state? It's also 11. What about what's happening here? If we have a charge or a plus, what have we done? We have stripped one of the electrons away. So in this, we actually have 10 electrons. Okay. So the electron configuration for this is different than the electron configuration for this because we have one less electron. So let's write out the electron configuration using the quantum mechanical model. It would say that it's 1s2, 2s2, 2p6, 3s1. Now we know that it forms a plus charge. When looking at this thing, this configuration here is a noble gas. This is what's giving us the problem. It's this one extra electron that's like, ugh, making it so unstable. So what tends to happen is this will fall off. And then what are we left with? 1s2, 2s2, 2p6. What is this electron configuration? Well, look at sodium and subtract 1 electron. We're at neon. So the positively charged ion of sodium has the same electron configuration as neon. That's why it forms that charge, because it wants to become like a noble gas. Let's look at fluorine. Okay, so we've got F versus F with a minus charge. Fluorine's in that second to last column. Everything in there likes to form a -1 charge. Protons for fluorine, 9. Protons for electrons. Electrons for fluorine without a charge. My daughter is like banging at the door right now as we lecture here, so I'm sort of multitasking. Okay, we've got 9 electrons as well because it's not charged. If there's no charge, you can assume the same. Now this guy down here, protons, also 9. Electrons have shifted though. We've got a negative charge, so that means that we've added an electron. So let's go through the electron configuration of fluorine first. 1s2, 2s2, 2p5. Oh, it's so close, isn't it? Isn't this so close to being complete? If I just had one more electron, it would have the noble gas configuration of neon. So what fluorine does is it steals an electron from out there in the ether and gives itself this configuration when it's charged. What is the configuration of this? Neon. So there are a lot of elements that when we charge them, they can become like neon. Look at oxygen on your periodic chart. Oxygen forms a 2- charge. What does oxygen like to do? Grab 2 electrons. If we hop 2 steps forward, it becomes like neon. Okay. What about aluminum? Aluminum on your periodic chart likes to form a 3+ charge. So what does aluminum do? It hops back 3 steps to get you to neon. That's why they have a predictable charge. This gives us that predictability power. That's why I can say everything in column 1 forms a +1 charge. So hopefully you believe me a little more now on why those charges are what they are. So again, everything wants to become like a noble gas. These things are particularly stable. So things are going to gain or lose electrons in order to get like that. So our alkali metals are column 1. They all have one valence electron in that outermost shell. So what do? They just ditch that valence electron, and then they become like the noble gas before them. Alkaline earth metals, column 2, they have to get rid of or shed 2 electrons in order to become stable. If we go to the other side where the halogens are, fluorines, those are so close to having a complete outer shell, it would not be easy for them to strip 7 valence electrons away. It is just much easier for them to absorb 1 electron and complete the set. So again, here are our predictable charges. And hopefully that's making a little bit more sense now that you know the electron configurations for them. So I'm going to give you one. I want you to do and I don't want you to do abbreviated electron configurations, okay? I want you to do the electron configuration for phosphorus. And I also want you to do the electron configuration for phosphorus with its 3- charge. All right, so phosphorus, 15, 1s2, 2s2. Hopefully you're starting to like even memorize this ordering. You say it so often, you're like, I can like do it in my sleep. 1s2, 2s2, 2p6, 3s2, 3p, 1, 2, 3, 3, 3p3. Okay. So if we're going from phosphorus to its ion, know that the negative is telling us that we're adding 3 electrons. So I need to pump this up with an additional 3 electrons. So if on an exam, it asks you for the electron configuration of the ion, just know that's different than the electron configuration of the ground state. So we got 1s2, 2s2, 2p6, 3s2, 3p6. It actually now has the electron configuration of argon. So you know you've done the ions configuration correctly if it is in fact like a noble gas. You won't have one of these become something that isn't a noble gas. Any questions on that, on charged particles and how to do charged particles? Okay. Great. So last thing in this chapter is talking about periodic trends. So there's 3 periodic trends that we want to look at. You want to have your periodic chart out. You may want to take some notes on this. So the first periodic trend is atomic size, like how big are the atoms from the center out to the farthest electron. Well, as you move to the right across a period, the atomic size will decrease. As you move down, the atomic size will increase. So the lower left-hand corner of your periodic chart, where number 87 is, sometimes they call that one Fat Frankie, that's your largest. And it will decrease in size as you move towards the upper right-hand corner towards fluorine. The size as you move up and down is dependent on the quantum number, right? So the 2s is going to be bigger than the 1s. So that's why moving down, it gets bigger. Why does it get smaller as you move across? Because if you think about it, if we're looking at like lithium, beryllium, boron, carbon, nitrogen, oxygen, we are getting, like, aren't we getting more electrons? Aren't we getting more protons? Shouldn't we be getting bigger? Well, we are adding electrons, but the electrons are in the same shell number. It's like filling up the same onion layer. We're also adding protons, which the protons have a positive charge, so they pull the electrons closer. They hold them closer. So carbon has more protons to hold that onion layer closer than lithium does. That is why it gets smaller as you move across. So here's an image. They don't include Fat Frankie here, but we can include Fat Frankie. So if I was to look at, let's say we've got oxygen and aluminum. Which one is bigger? Oxygen and aluminum. We would say aluminum. Aluminum's bigger. Okay, it's all just in reference to who's closer to this side. So you want to be able to like order electrons. The next thing is ionization energy. Ionization energy increases as you move to the right and decreases as you move down. Okay, so the highest ionization energy is the upper right-hand corner. So where fluorine is, that's the highest ionization energy. The lowest ionization energy is Fat Frankie. Now, what is ionization energy? Ionization energy is the amount of energy required to take an electron. So think about fluorine's electron configuration. 1s2, 2s2, 2p5. Are we going to take an electron from here and make that 4? No, this thing wants to absorb an electron. It would require a lot of energy to take that thing. So that's why the highest ionization energy, upper right-hand corner versus, let's say we're looking at Fat Frankie. I'm not going to do the whole electron configuration, but I'm just going to include the last one, which is 7s1. This is like, this onion layer is like so far from the center, those electrons are practically falling off of the atom. And if we get rid of this thing, we'll have a complete electron shell like the noble gas before it. So it's very easy to take an electron from there. So again, ionization energy lowest down here, real easy to steal electrons from here. And think about metals in general. Don't metals like to give up electrons? Isn't that the whole idea? One of the classifications of metals is that they're cations. They like to get rid of all these things. These guys over here are greedy for electrons. They want to take electrons. They don't want to give up electrons. So it would require a lot of energy to pull an electron from fluorine. Take a lot of energy to pull an electron from one of the noble gases. They're already stable. So why would they want to give an electron up? Doesn't mean you can't do it. It just is a lot of energy to do it. Last trend is metallic character, which should hopefully feel like a no-brainer. Fat Frankie in the lower left-hand corner has the most metallic-like character. All right, so the closer you get to Fat Frankie, the more metal-like you are. It decreases as you move up and to the right. Is OG a noble gas? No. on your periodic chart, do they have it named? Are you talking about 118? Yes. So those are synthetics. So it would have a configuration that is stable. So if we're looking all the way down the very last one, you can see 118. It would have the electron configuration of what we would say a hypothetical noble gas is, but that's a synthetic that they've made in a lab. It requires an immense amount of pressure and usually a really cold temperature to even keep that thing stable for like a microsecond. So that atom, because it's so big and those onion layers are so far from the nucleus, it sort of just falls apart. Make sense, Harley? Yes, no, maybe so. It shows it as green. Yeah. Oh, I see. Yeah. So this is a synthetic though. This a lot of these guys down here are not. They don't really exist in our. I mean, maybe like in the center of a star somewhere we can see that, or a black, maybe more of a black hole. But in our reality, we don't work with those a whole bunch. Radon is usually the biggest noble gas that we play around with. Cool. No worries. No worries. We got time on our hands. We're in a good place right now, lecture-wise. So, okay. So we talked about so the metallic-like quality. All right. So lower left-hand corner, most metallic-like, upper right-hand corner, least metallic-like. It follows the trend of your zigzag line. So down here, biggest, most metallic-like, lowest ionization energy. Over here, smallest, highest ionization energy, least metallic. Okay, so when looking at this, I would say that cesium is more metallic-like than calcium. It has more metal-like properties. Iron has more metal-like properties than aluminum, right? Anything that's moving closer to that corner. All right, well, there we go. That's it. We're done for today. We're done for the week. Woo. So we're in a good, yeah, right? So we're in a good spot for next week. Next week is going to be interesting. It's a very visual lecture. We're going to be looking at molecules in three-dimensional structures. So I'm not really sure how I'm going to portray this to you guys over the internet. Maybe I'll get some like sticks and marshmallows and we can try and make some figures. You may want to have some sticks, like if you've got toothpicks and marshmallows, you may want to have some so that we can try and make some of these shapes. Because what we're going to be doing is taking these atoms and sticking them together, but we want to be able to sort of see them in 3 dimensions. If you're an artist and you think in 3 dimensions already, then you'll be fine. Okay, so awesome job. Let me know if you have any questions. Otherwise, we are done for today. I'm going to try and get a run in before my next lecture. But feel free to stay around if you have any questions. Okay, bye guys.